I'm Dr. Yogesh Kumar, Assistant Professor in the Department of Physics, Hansraj College, University of Delhi. So today we are going to discuss about a very beautiful experiment of quantum mechanics, that is photoelectric effect. And in this experiment we will study some experimental observation, like we will see the effect of intensity of the incident radiation on the photoelectric current. Second, we will study the photo current versus wavelength of light. And third, we will discuss the maximum energy of photoelectron versus frequency of light. So this is the experimental setup. So first we will define this. What do you mean by the photoelectric effect? So when the electromagnetic radiation of sufficiently high frequency fall on the metal surface, then electrons are ejected from this photosensitive plate, and this phenomena is known as the photoelectric effect, and the emitted electron are called photoelectrons. So the whole range of the electromagnetic radiation from gamma rays, X-rays to ultraviolet, visible region and infrared rays produce this effect. So this effect was first time discovered by the most famous scientist Hertz in 1887. Further, the experimental study was undertaken by the Holbach in 1888. Then in 1899, Lenard showed the carrier of the electricity emitted from a metal surface under the action of ultraviolet light were electrons. So in a simplest way, you can see that whenever the suitable frequency of radiation fall on this metal surface, electron are ejected with certain kinetic energy depending on the certain condition, and these are measured by the emitter here, uh, and this whenever we increase the potential, then electrons are having the sufficient kinetic energy so that it can fall on this anode plate and produce the sufficient current here. So here we will first see how this photoelectric current depends on the intensity of incident radiation. So here you can see the straight line curve, which shows that the number of photoelectron emitted per second by the surface is directly proportional to the intensity of the incident radiation. The current is due to the flow of all the photoelectron emitted per second from the surface. So this photoelectric current directly depend on the intensity of the incident radiation. Second, as you can see here, there is the photoelectric current is completely independent on the wavelength or frequency of the incident radiation. And in third curve, we can see the effect of frequency on the stopping potential. As you can see here, it is seen that the frequency of the incident light is increased, the stopping potential for a given surface, metal surface increases. So as the frequencies increases, then stopping potential is also increases. So light of different wavelength can be used by putting appropriate color filter or colored glass in the path of light falling on the photodiode. So here the photoelectric current is directly proportional to the number of photoelectron per emitted, and here the stopping potential is also depend on the frequency of the incident radiation. You can see this famous equation here, which is also called as the Einstein-Planck equation, where the maximum kinetic energy of the photoelectron depends on the frequency of the incident radiation, not on the intensity of the incident light. In the same way, the kinetic energy of the electron is also dependent on the stopping potential here. And this W is the work function. It is also called as the threshold frequency, which is taken as the minimum frequency of the incident radiation that can cause the emission of photoelectron with zero kinetic energy from the surface, and below which no emission of electron are occur. So using this, this kinetic energy of the electron and the stopping potential are related to each other, which is also directly proportional to the incident frequency of radiation, which is given by this equation. So if you plot the frequency and stopping potential curve, it will give me the straight line by using this equation, and we can easily compute the Planck constant. And this Planck constant was first time so Millikan's in 1916 determined the value of h from the slope of the straight line graph of EV not against this frequency. Thank you so much.